Hi there, and welcome to part 2 of our first lecture on the calculus of variations. Now, last time we talked about a particular problem where the goal was to minimize the distance between 2 points in the plane, or find the curve between 2 points in the plane such that the distance traversed along it is stationary. Now, we want to construct a slightly more general problem. What does that problem look like? Well, very similarly, we start off by identifying 2 points in the plane. We call them P and Q. We connect them with a straight line y of x, and we identify points A and B, their endpoints on the x-axis, and points YA and YB, their endpoints on the y-axis. So the goal here is to minimize a functional on this curve that's more general than the distance functional we identified before. So we define this functional f of y. Now that's just the definite integral from a to b of some function lowercase f of y, that's the curve, y prime, its derivative, and x, all with respect to x. So this is a more general functional. And the problem here is, what is the function y of x that makes the functional capital F of y stationary, right? So same as our problem before, but we just abstracted away that square root of 1 plus y prime squared into this more general object f, which is some function of y, the first derivative of y, and it might have some explicit dependence on x as well. Now, immediately, there are two questions that seem to come to mind. Firstly, what do we mean by stationary, right? So really, I just want to labor on this word stationary here. So essentially, I'm just going to ask the question, what on earth do we mean by stationary? By stationary. And the answer to this question really comes from, one, investigating the meaning for functions. So what does it mean to make a function stationary? And then we just follow our nose and generalize. So we just generalize after identifying the salient aspects of this definition. We generalize to functionals. And secondly, maybe slightly more subtly, depending on your taste, we've identified a stationary point, but the question we asked before, really the geometrical question, was for a minimum. We wanted the curve that minimizes the distance functional. How can we be sure that the stationary point is also a minimum? So how can we investigate the nature of stationary points? Of functionals. Now, this is what we're going to take up next. So part one, we're going to take up our study of the meaning of stationarity. So what does it mean for a functional to be stationary? That's going to occupy us for the next three lecture sections, or the three sections of this lecture. However, this second question is kind of beyond the scope of this lecture series, in particular because usually we can tell whether we have a minimum or a maximum on physical grounds. So we can usually tell on physical grounds. The distance function is a perfect example because if you remember what that looked like, well, we think the answer is going to be a straight line, and we're correct. We just need to prove that more generally. But think of all the other curves we could possibly have, right? Think about anything we could do to make that bigger. I could draw this curve here. That would be longer. It's clear that this kind of bulges out. I should be more careful about my language there, but you can see, it bulges out. So clearly it's longer than that one. But then it's like, what about this one, right? What about that one? What about this one? This is even longer, right? What if I do the same thing? What if I keep playing this game? Will I ever arrive at a point where I can't make it any bigger? And you can kind of see, by playing this game longer and longer, that you can't really do anything. I can do any kind of awful curve I want. And it seems like the distance function along this curve is never ever going to get uh, any shorter, and there's no way to uh, have a cap on how long I can make this. I can make it arbitrarily complicated. I can bulge it out as far as I want, and there's no limit on how big I can make it. But it does seem that there's a point after which it won't get any shorter. So there, we believe on physical grounds that once we found a stationary point, we think it's going to be a minimum as well. However, there do exist techniques for analyzing the nature of stationary points of a functional more rigorously, but those are just things we're not going to take up in our study of calculus of variations right now. So next time, we're going to come back to this question, what do we mean by stationary? Because we're going to investigate it in the simpler case for functions.